Hello and welcome to today's video. In today's video, we're gonna be looking at practical applications of higher kind of types. If you don't know what the higher kind of types are, please see the video. I'll link it in the description below. But if you have seen that video and you were wondering, well, this all seems very nice, but it's very theoretical. How can I apply it in practice? This video intends to show that. So today what we're gonna do is we're gonna be solving a problem which sounds like this. So imagine you have some game configuration. There's some hit points or names and stuff like that, which you receive during the login procedure of your game. So you launch your game, you connect to the server sends you all of this configuration. Now, during the gameplay, that configuration might change. Maybe you've released an update or something. And what you would like to do is not send everything over to the client again, because that might be a lot of data, especially if you send it to every client at once. What you want is you want to only send the difference, the actual values that have changed in the configuration, and you want to do that easily. So that's the problem that we're going to be solving today with the higher kind of types. With that said, let's get directly into it. So as I've mentioned, we have a game configuration class here, and it's just some configuration for the game, and it is parameterized with a higher kind of type. So in our case, we'll be using these two types, ID and option. So an ID type is a really simple type. It's basically just a struct that holds one value. But it is a higher kind of type, so that is important to us. Now, the option type represents an optional value. So it can be, you can have a value or you can have no value. So that will be used to calculate the differences. So essentially we have this game configuration and we just have two properties. And I've declared the properties with different types. So we would see how this works across types. So we have the hit points, which are represented by integers, and names, which are represented by strings. And essentially, if you have your standard configuration, you can create it like this. So you have this GameConfig.apply method, and apply is created by our record type and the constructor flags.apply here. And you just say, I'm gonna have 100 hit points and the name is gonna be Archer, right? So you have this configuration. Then let's say you do release an update and here's the new configuration, and you have both of these in the memory. So the new configuration is just the old configuration, but we're saying that we're actually gonna have 200 hit points instead of 100 hit points. And this method is generated by this withers flag here. And as you can see, the new configuration just equals the old configuration, but instead of, the name is the same, but the hit points are updated. So now what we want to do is we want to compute the difference between those two. And to do that, we have to use this zip method that we wrote, and we say basically, here's the old config, here's the new configuration, and zip those two together. So if you don't know what zipping is you can actually think of it as like this zipper. It has two parts, and then you zip it together with some zipper function, which is this thing, and you get something else. So let's take a look at each of those. So first, let's take a look at zip. So what does zip do? It essentially takes two game configurations here, but take notice that the higher kind of type here, the witness for the higher kind of type, is different for those two. And what we do is we also have a mapper. And this is not a regular function. This is a higher kinded function here, and we'll get into that in just a second. But essentially what we do is similarly to what we would do with regular functions. So basically we say, let's create a new game configuration, and the hit points is going to be, we're going to apply the mapper to the hit points from the first configuration and then the hit points from the second configuration. We're going to do the same thing with the name. Now let's take a look at what this apply function does. And here we can see that this thing is basically the same thing as the regular function from the system namespace, but instead of transforming values like integer or string, it transforms the functors. So it can take, for example, an ID functor and turn that into an option functor, or maybe from an option functor to some other functor. So as you can see, it takes in some value of type A wrapped in a higher kinded type with the witness type 1. And then it takes the value of the same type A, but in another higher kinded type. And then it just, uses those two to produce some result of type A, and resulting in a different functor. So WR here just stands for witness of result. So that might be not very clear. So let's look at the actual function K, which we have here. So let's take a look. So this is a function K that computes the difference between two game configurations. And basically it takes an older version and the newer version of a value and then returns sum if those two versions are different, or none if they are equal. So if you look at the type signature, you can see that this takes two ID functors here, and the result functor is an option. And as you can see here, we get this ID, the first value wrapped in ID functor here, the second value wrapped in ID functor here. Then what we do is we basically unwrap it, because we know that ID is just a wrapper. We turn this from the higher kind to the concrete kind into the ID, and then we just access the value there. And we do the same with the second value, and then we have an equality comparer here, which can compare these two values, and we just compare them and say, okay, so if they're equal, then we're gonna return a none case, but if they're different, then I'm gonna return the updated value. So what this does is, after you apply this, you get this game configuration, which is now wrapped in an option type instead of ID type. And you can see that this game configuration difference is now equal to this, where hit points, because they were different, is equal to sum 200, whilst name, because it was the same name, is equal to none. So when we have this, this is the difference that we actually have. Now the second part of it is to actually apply the difference to the existing configuration. So we have this existing configuration, and we want to apply the difference to get the updated configuration. So basically we just use this zip method again, but now we do that, we use it with a different function, with different higher kinded function, and we use the difference apply function. So basically we take a value and maybe an updated value. So this is the value, and this is maybe an updated value, and we return the updated value if it's present, so if it's sum, or old value otherwise. So again, what this does is basically we have this higher kind of value, we narrow it down into an option, then we fold over that option. So if we don't have a value, if we do not have a value, we just use the old value from here. But if we do have a value, if we do have an updated value, then we just use that. And to use that, we need to wrap it into the ID functor, because that's the required type signature. So with this function here, we can basically call this zip, and then we get this diff applied configuration, which, as you can see, is computed correctly. So we have the hit points, which is now ID of 200, as here in new configuration, and we have the name, which is kept the same from the old one. In fact, essentially, this is the same thing as the new configuration. So how is this useful in practice? In practice, you would have these, you would have this, for example, you would have the configuration change handler in the server, and when the server detects that the configuration have changed, it will have these two values. It will have the configuration value, which is the old configuration, and it will have the new value, which is the updated configuration. Then it would be able to compute the difference here and then send that over the network to all of the connected clients of your game that are currently playing the game. Then those clients, they know the old configuration, and then they get this update, and then they can apply the update to get this new configuration and store it locally, and then use it from that standpoint, from that point onwards. So let's take a look at how it looks if you actually serialize it to JSON and deserialize it. So here we go. So we have this JSON test. Essentially, we can try, first thing that we do is we have this JSON string here, which is just, there's hit points of 100 and the name of Archer, and we deserialize it with this parser. So we can take a look at the definition of the parser, and we can see that it basically is a parser from JSON value, and it expects to have a JSON object, and then it says, oh, let's try parsing it. Let's try getting an integer of hit points at the key of hit points, and then let's wrap that into the ID functor, and then let's get the string and the key's name and wrap that in the ID functor. So with that, you get a parsed configuration here. So if we specify the type explicitly, you can see this is a game configuration of where the functor is ID. Now serializing to the other side happens via this method called toJSON, and we can take a look at it. And essentially, this takes any game configuration object and turns that into a JSON object. And to do that, it needs these two things. So it needs this value to JSON function, and it also needs a functor. And we'll see why. So what it essentially does, if you take a look at value to JSON, basically it's a function where we give it a key name, which is a string here, and then we give a JSON value, which is wrapped in this functor of W, and then we get a JSON object out of that. And why we need this is we basically want to reuse the same code for serializing both the normal configuration, which is you have to send all of the values, and we also want to reuse the same code of serializing to JSON for sending only the difference, which should send only the values that have changed. And we'll take a look at how that works just in a second. But yeah, what we do here is basically we say, okay, so let's turn this value into JSON, and it's going to be named hit points. And then let's take this integer from here and let's map it using the functor. And we take that integer hit point, we take that integer from here, and we turn that into a JSON value. Similarly, we do the same thing with a name, but we turn this into a JSON string. So when we have a full configuration, when we need to send everything, what we do is we have a name here, and we have the JSON value, which is wrapped in an ID type. So again, we narrow that, and then we extract the JSON value, and then we just create a JSON object out of one key value pair. And this code then, remember, this returns a JSON object, so we can merge those JSON objects using a plus operator. So basically, we get a bunch of JSON objects, each holding one key value pair, and then we join these two things together, getting a JSON object which now holds two key value pairs. If you're wondering why so complicated here, well, it will be very useful when we're sending diffs. So after we serialize this, you can see that the result is basically the same thing as we had previously, where we parsed the JSON. Now let's try deserializing the difference which the server sent us. So in the difference case, you can see that the name is not sent and only the hit points are sent. So we're not sending any data that isn't required to save traffic, because that's the whole point of this. Otherwise, we could just send the whole configuration and be done with it. To parse that, we basically need to not error out on missing properties like name. To do that, we have this different parser, which instead of parsing into ID functor, parses into an option functor. And what this does is basically says, if a property is missing, no big deal, just return none. And if it's not missing, then return some. So the only difference here is here you wrap values with ID, here you return options. Now, after parsing this, well, you will get exactly this. So this thing should equal the parsed value should equal this. So the hit points will be 200, while the name will be not specified. So by parsing this, we get this value. And then we would apply this value as I've shown previously. And then the final thing to know is how do we serialize this into JSON? And this is where the interesting thing becomes. So this config difference is made out of options, where the values are options instead of IDs. And we can reuse the same to JSON method because it's higher kinded. It doesn't care about the functor type that it's in. It only cares that we have a functor for that witness. And what we get is here we get this value, but now it's not in ID, but it's in the option. So previously we had this. Yeah. So previously this was an ID. In our case, this is an option. And then we say, okay, so if the option is not specified, if it's none, then we can just return an empty JSON object because we're not sending anything. And then if it's some, then we're gonna take this JSON value and then return again an object with one value in it. And now, if you go to this toJSON thing, you will see that for example, if nothing is actually changed, all of the values in this game configuration is none, then this will return an empty object, and this will return an empty object, and an empty object plus an empty object is an empty object. But if any of these will return a changed value, then we will get the actual data in that object, and it will not be an empty object. And we can see exactly that. So you can see after serializing this config difference into JSON, we can see that the hit points are serialized, but the name is not serialized because hit points was some value and the name was an empty option, a none here. So, and basically now you have this infrastructure here, and if you just want to add any other properties here, it is fairly simple to do that, because all of this machinery, all of this code does not really care about all of these internal types, as long as you provide the appropriate parsers for JSON and converters to JSON. So that's basically it. I hope this explains and demonstrates the practical use case of higher-kinded types in code. And I know that this might be a bit hard to follow, so I'm just gonna put this code into GitHub, and I'm gonna link it in the description below so you can analyze it and take a look at it and study it, And if you have any questions, as always, hit me up in the comments, and see you in the next video.